know how you, when you put in the struct node, it wanted like bracket 0. It didn't work if I didn't have the bracket 0.
Yeah, bracket 0 will work, but it's not necessary.
It was asking for like some sort of array without it.
So um, 205, right? So this should work if you're using the arrow notation, right? It will also work if you say in bracket 0 dot data, right? Because technically in is an array, but that arrow notation is basically saying thing that in points to dot data, right? Same as in arrow data, or in bracket 0 dot data. Does that make sense? So were you trying just in dot data?
Yeah.
Okay, yeah, so that'll complain because in's a pointer. So yeah, there's our struct node. I did not need standard IO.h, doesn't hurt to include it. But I'm not doing any IO. Oh no, I'm using null, so I do need standard IO. So yeah, this takes the data piece, multiplies by 2, stores it back in the data, and then it sets the next piece to be null. That's all there is to it. All right, so ODP 206, we're going to continue building up this functional behavior. So define a struct node and then write a function named new node, which basically does the process of creating an empty node, giving it a data value, setting the next field, and so on. So new node has a prototype like this. It takes a single integer. It returns a pointer to a struct node. Okay, and its behavior is create a new node using malloc, set the data field equal to whatever that integer that's passed in is, okay, data, set the next field to null, and then return the address of the new node. So this is something you would call from, say, your add function when you decide you want to make a new node. Call new node. This is kind of what your get node function did in PA1. Right, get node returned an index of a new node that you could store in the array. This is returning the address of a new node. It's also initializing the data value in the next value. So standard test bed, standard way to compile, standard way to assess. And this will be like one more line of code than ODP 205 had, maybe 2 more lines. So you want to call malloc to create a new node, but remember you need to test the return value from malloc just like you did in PA1. You need to make sure that it's not this magic flag null saying that there's no space left. If malloc returns null and you try to set the data field of null, you'll get a seg fault. That's not going to happen unless you happen to be assessing and the machine is out of memory for some reason. But make sure you check the return value anyway, and then it's not equal to null. So I'd like to play with this, and I'd like to start writing some code that just builds up some linked lists, not necessarily something in PA2, but just something to sort of let us start manipulating nodes that are created dynamically in memory, and then we'll look at PA2, but it's basically PA1 with one small twist. All right. Alright, so here's some code from yesterday. Alright, so we put together an init function yesterday that allocates a sentinel node and then sets its data to 42, sets its next to null, and returns that address of that sentinel node as its function value. So in our main program we can define a linked list, which I'm calling list, and we can say list equals init, and that'll be a pointer to the sentinel node. So let's make a get node function. Which will be similar to our get node in PA1. So get node is kind of like ODP 206, but it won't be exactly the same. We're not going to actually initialize a data field here. So what does get node do in PA1? It moves through the array of struct nodes. It looks for an entry where valid is equal to 0. And if it finds that, it returns the index of that entry. And it tells the caller, here's a place where you can store a new node. And if it gets to the end of the array and it hasn't found an unused block, it returns my null, which says there is nowhere left to store a new node. Okay, that's what get node is going to do. But we're not going to search an array, we're going to let the system do that. That's what malloc does. So all we really need to do is return malloc size of struct node. So size of struct node is how many bytes we need. Malloc of that will return a block containing that many bytes available. If it's out of space, it'll return null, and we'll just return that value in either case. So our get node from PA1 is like one line here, and I'll prototype that. Alright, so now we got two functions, init and get node. So we are going to call init, and that's going to make a sentinel node with 42 and null. So let's build a list. Let's make another node that has 10. So let's call get node and let's save its value in what we're going to call first node. And then let's make a second node, and then let's make a third node. So we're going to have a first node, second node, and third node. And let's build a little 3-node list by hand. So I want first node's data to be equal to 10. So how do I say that?
First node arrow.
First node arrow data equals 10. First node is a pointer to a node. First node arrow data says take the thing that first node points to and look at its data field and set it equal to 10. So first node arrow data is this block right here. right? That's what this block is. And we can do the same thing for second node and third node. So second node data is 20, third node data is 30. So we've set up these data fields, but we just have 3 nodes sitting in memory. They're not connected in the list yet. So to connect them into a list, we want to have this point to first node. So how do we set up this arrow so that the sentinel node points to our first node? So we want list to point to first node. So what's the name of this pointer block inside the node called list? Not exactly next. Yeah, in that block it's called next, but what's the expression we would use in C to access this block? Yeah, list arrow next. Right, list is this block, list arrow next says see what list points to, that's this rectangle, and the dot next field, that's the lower half of the rectangle. So list arrow next. And what do we want to set that equal to? Just first node, right? First node is an address. So this is where in PA1 we would have said list bracket 0, close bracket, dot next equals whatever the integer was that we got when we called get node for first node, right? First node would be an index, it would be an int. We'd set list next equal to that. First node arrow next, well first node is here, first node arrow next is this block down here, and what do we want that to be equal to? That's just equal to second node. And then second node next should be set to be third node. And then how do we terminate the list? Yeah, so set the next down here equal to null. So this is third node arrow next. Is just equal to null. So that should build a little linked list with a sentinel node and 3 data nodes inside our memory. So let's GDB it. Alright, so I'm going to say next, so it will run the whole init function and then come back to the debugger at line 18. So list should be a pointer to a sentinel node. If I look at list, it's 60, 20, 10, our favorite hex number this week. So list is 60, 20, 10, and I'm going to use hex today. So I'm going to build sort of a little memory map here. If I say print star list, it tells me the data value is 42, the next value is 0. Oh, I don't like that next value. No, that's okay. All right, so first node is going to be equal to get node. If I look at first node right now, it's kind of whatever, right? If I print star first node, the data value is some big negative number. The next value is totally ridiculous, right? Because we haven't initialized first node yet. We haven't executed line 18. So I'm going to say next, which will make this call to get node and assign the result to first node. And now if I look at first node, it's got a data value of 0 and a next value of 0. And if I print first node, it's 60, 20, 30. So first node is down here at 60, 20, 30. All right, we're going to set second node to be get node. We're going to set third node to be get node. So if I print second node, that's 60, 20, 50. And if I print third node, that's 60, 20, 70. So what I'm doing over here is I'm building a memory map. So these are addresses. And we're going to, did I leave enough space? So 10, 14, 18, 1C, 20, 24, 28, 2C. All right, so what do we got? Second node is a 0 and a 0. Third node is a 0 and a 0 also. All right, so we're about to set first node data to 10 and set second node data to 20 and set third node data to 30. So first node is 10, 0, and so on and so forth. So let's look at 60, 20, 10 going forward in memory. So 60, 20, 10 contains a 42. Decimal. That's our data field of our first node. And then 0, 0, 0, 0, 0, and then 60, 20. 60, 20, 28 contains a 40. Contains a 33. That's probably random. So 60, 20, 28 contains hex 21. That's the number 33. And 60, 20, 30 contains the number 10 in decimal. And then 60, 20, 48 contains another 33. 60, 20, 50 contains 14 hex, that's 20 decimal. And then 60, 20, 68 contains 33. I don't know where those 33s came from. And then 60, 20, 70 contains 1E, that's 16, and 14, that's 30 decimal. And then 60, 20, 88 contains something weird. All right, so there's our sentinel node's data. This is garbage. First node's data, garbage. Second node's data, garbage. Third node's data, and garbage. Right, and we are about to execute this instruction. List next equals first node. So first node is 60, 20, 30. List has a next field of 0 right now. If I just execute one instruction and I print out what list is, now the data value of list is still 42, but the next field is 60, 20, 30. That's the address of our first node. So if I go back into memory, I look at 60, 20, 10. That's got a 42, all right, that's our piece of data. The next location is 0, the next location is 60, 20, 30. The next location is 0, 0, 0, our weird 33, and a 0. So our sentinel node looks like this, 42 space 60, 20, 30. This is the data field of the node, this is the next field of the node. And that number in there tells us where in memory is the next node. Okay, so let's execute the next instruction. First node next equals second node, and second node next equals third node, and third node next equals null. So now if I print first node, its next field is 60, 20, 50. $60, 20, 50 is the value of second node. It's the location where the second node is stored. Second node has a data value of 20, a next field of 60, 20, 70, which is the value of third node, which has a data field of 30 and a next field of 0. So if I look at my memory, starting with location 60, 20, 10, there's a 42, there's a space, there's 60, 20, 30, that's the address of the following node. And then all of this is just kind of filler. 60, 20, 30 is our first node, data value of 10, next value of 60, 20, 50. And then filler. 60, 20, 50 is our next node, that's a 20. A space, and then a next field of 60, 20, 70. And then 5 words that are just hanging out. And then 60, 20, 70 is our last node, data value of 30. Next field of 0, and then 5 bytes that are filled with whatever, and that's the end of our list. So that's the actual contents of memory. This is what it means to us. right? So this is list arrow data, list arrow next. First node arrow data, first node arrow next, and so on. So in code, right, this is easy to set up. Right, we initialized our Sentinel node with a init. We created new nodes by calling getNode. We set up data values by saying node pointer arrow data equals. And then we connected these pieces together by setting the next fields explicitly. And so this has given us a linked list. And as long as we know the address of the Sentinel node, which is the variable called list, we can manipulate this list just like we've been doing in PA1. So let's make a basic print function. So we'll make a print. It'll take a struct node pointer and it doesn't return anything. And let's just traverse the list. So node is the name of the Sentinel, right? That's what we're passing to it. We're saying print list. List is the Sentinel node. So let's print out the Sentinel's information anyway. We don't normally do this, but since we're just exploring this, let's print out the Sentinel's data. So if node is the Sentinel's data is node arrow data. And the node's next field is just node arrow next. So that's not part of our official list, but we'll print it out just for kicks. So how do we loop through and print our entire list? So that's what our list looks like. Node is the Sentinel node. So to move down the list, to make node point to the next thing in the list, it's just this. Node equals node arrow next. So that will change node to be the next node. And we can print node arrow data. And then we can do node equals node arrow next. Print node arrow data. And then move node again. And I'm doing it this way on purpose. So now node is pointing to the last node. We still want to print that data. So that'll print a 30. Node equals node arrow next. So now node is equal to null. And that's where we want to stop, right? If we try to print node arrow data now, we'll try to access memory location 0. That's a seg fault. So when you're trying to turn this into a while loop, sometimes it's useful to sort of write out each of the steps you want without a loop, and then just think, how can you bundle it into a loop? Well, I know I want to do node equals node arrow next and print node arrow data. So I could just throw that in a while loop. But the last thing I want to do is my node equals node arrow next, and then notice that node is equal to null. So this suggests what I want in my while loop is print node arrow data and node equals node arrow next. And I want to stop that when node is equal to null. So I'm going to say while node is not null. But I still want to do this once in the beginning, right? So that I move past the sentinel to my first data node. So you can get here however you want, and there's a variety of ways you could do this. I could just throw this whole thing in a loop, and inside the loop I could say if node's equal to null, then break out of the loop, right? Or I can move once and then in the top of my loop check to see if node is non-null. There's different options here. Do what makes sense to you. So we're going to point to the first actual node of our linked list, our first data node, or null. So while node is not null, this means node is an actual real node, so we can print out its data. So I'll print out my node arrow data. In the end, I want to print these all on one line, but remember, if you don't put a new line at the end of your print, you may not see your output if you segfault. And since there's a good chance we're going to segfault in here, every time I print something, I'm putting a new line at the end. Otherwise, I might print 3 things and then get a segfault, but since I didn't put a new line, I won't see any of those 3 things. And I might start going on a wild goose chase.
There's not a different escape character you can use to like force it out with that?
You can say f flush parentheses standard out.
Okay.
And that'll force it out also. Alright, so I'm going to print the node's data and then move to the next node. And that's the end of my while loop. So it's a 2-line loop. Print the data, move to the next node. Print the data, move to the next node. And my while condition says if the node doesn't exist, it means that when I move to the next node at the bottom here, I didn't find a node. So I've already printed the data from the last node, in which case my print is done, so I'll just return. Alright, so we'll make a call to print in our main program. Does this seem reasonable? So we run main, and there's the data we stored in our list. And my memory address is totally different from what it was before. Before it was 602010 hex, now it's BA2030 hex. Now it's 1BB3030. Alright, but we don't need to know what that number is because we have a variable called list, which points to our sentinel, and the sentinel's next points to the first node. So I use 3 variables here: first node, second node, third node. But I didn't have to do that. They could have all been called the same thing. Because these variables are just pointers to memory, but they're going to point somewhere different each time that we assign them a value from getNode. So let's make a new version of this. So let's forget about all of this. So let's just make a linked list new node equals get node. Set the data to 10. Alright, so new node's a new node from get node. I'll have list point to that new node. I'll set the data value to 10. And then what should I set the next field to? Return from get node. So now new node next is equal to the address of a new node. And I'm going to change new node to be what that is pointing to. So that's the address of the second node. Give the data value a value we want. And let's have the next field point to a new node. And then let's change new node to point to that third node, yeah.
Shouldn't those be new node arrow data and new node arrow next?
You're right. Thank you. Cool, much better. Thanks. So we can keep doing this. Set this to 30. Get node. Let's just do it once more. And for this last node, we'll set new node next equal to null. So I've got my original list, and I've got one temporary node called new node. And I keep doing the same things, new node data equals new node next equals, right? But each time I do that, new node has a different location in memory, so it's actually changing a different data field, right? A data field in a different struct node. And so that should make a list containing 10, 20, 30, 40. And if our print still works, that should print it out. If we write our comments correctly. All right. So run main 2, there's your list. Now if we wanted to do this where we were taking input from the user and building a list, it's pretty simple. Throw these 3 statements in a loop, and instead of setting the value to 20 or 30 or 40, read a value from the user, set the data value equal to that, set the next equal to a new node, and then move to that new node. And this will keep building a list, tacking things on to the end. So not tomorrow, but the next day's ODP, you'll start doing this kind of stuff in code yourself. You'll take a list and you'll start adding things or removing things from the middle of the list. And it's really just this kind of exercise, right? It's keeping track of what your variables are pointing to and then just adjusting the fields accordingly. All right, so let's talk mechanics. So back to our original main program, we had 3 variables, first node, second node, third node. We gave them each an address by calling malloc, right, which created a block of memory and allocated it to that use. And then we built up our list and we printed our data. So this was just our list of 3 numbers. All right, so here's the thing. When you call malloc, you're asking the system to find a block of memory that's available and reserve it for your use. It's giving you the address of the start of that block, and it's guaranteeing to you that nobody else will try to use that memory unless they're doing things they shouldn't do. Your system only has so much memory on it, right? If I look at my system right now, under memory, there's looks like a gigabyte of memory, and there's about 300 meg that's free, 100 meg that's free, 300 that's used. Memory is a limited resource, and if you allocate memory, that memory is not available anymore. Okay, so on Unix, when your program exits, any memory that you allocated is released. It's not like locked up forever. So once your program exits, somebody else could get that memory block. But suppose your program never exits. And suppose your program keeps allocating memory, eventually your system's going to run out of memory. So when does this happen? Well, for example, if your code is a web browser and somebody is using this on their home machine, chances are they open the web browser a few minutes after they boot and they never close it, because you don't want to close your browser because you got all your tabs and everything, right? So your browser stays open for a month. That's your program running for a whole month. If it's allocating a little bit of memory every few seconds and you don't release that memory when you're done with it, you can run out of memory. So these things are called memory leaks. A memory leak is when a program allocates memory using something like malloc and then fails to say, I'm done with this memory. And at the point when the program exits, if it's allocated memory that it hasn't released, that's called a memory leak. And it's considered really bad practice to have programs with memory leaks. And plugging these leaks is notoriously difficult, especially with a large complex program. And so typically, you'll find every now and then there's a program that people are complaining about online. This thing sucks up all my memory. Oh, you just have to kill it and restart it and you'll be fine, right? But if you don't do that, you can watch the system memory level just like drop lower and lower and lower. And when it gets too low, your system just runs really slowly. And usually the culprit is one program, and you just have to close that out or reboot, worst case. All right, so we have a tool we can use to find memory leaks. It's called valgrind. And starting with PA2, I'm going to ask you to use valgrind to check your code for memory leaks. And it's very easy to use valgrind. So I've got this program, main3, that I can run, makes a linked list, prints out the data, looks great. Before you turn it in, say valgrind main3. It'll run your program the same as usual, but at the end it will tell you how you did as far as cleaning up memory. So I run valgrind. It ran, it printed out all the data that I expected it to print. Heap summary, in use at exit 64 bytes in 4 blocks. It tells me I've called malloc 4 times, I've reserved a total of 64 bytes, and I have not freed them. And then leak summary, definitely lost 16 bytes. I lost 16 bytes of memory somewhere. indirectly lost 48. That means there's 48 bytes I've lost, but theoretically I can still get to in my code. Okay, any errors in here, anything that says lost blocks, any use at exit, those are errors. Doesn't mean your code's not doing the right output. Okay, your code can be working perfectly, but it means that there's some cleanup you need to do to release the memory that you allocated. Okay, so how do you release memory? Call the function free. And free takes the address of the beginning of a block of memory, and it will free it. So if you say something like m equals malloc, some amount of memory, when you're done with that block, say free m, and that'll release it. So in main 3, I use separate variables for each of my blocks. Very easy to free my memory at the end. So I can free first node, second node, third node. And let's see how that does. So now, all I have lost is 16 bytes in one block. I did 5 allocations, I did 4 frees, right? So right here, it's telling me kind of the punchline. I allocated 5 times, I only freed 4 times. So what did I forget to free? Yeah, the sentinel node. Now that's a hard thing to find sometimes, because I know that it's in a call to malloc, and I can search for malloc, and the only time I call malloc is inside a init or inside get node. So now I can search for every call to those, but it can become kind of a quagmire. So let's free list. All right, so main 3 still works fine. If I val grind it, here's what you want. All heap blocks were freed, dash dash, no leaks are possible. That's happiness. Okay, so I could run this program and it won't keep chewing up memory. All right, so we'll talk a little more about free, because if you try to free something other than a block that you got from malloc, you'll get all kinds of weird errors. So we'll play around with that a little bit. We'll look at the next ODP tomorrow, and we'll jump into PA2 tomorrow. Main 3 is the executable. So I compiled it from main3.c.